Okay, so what we're going to do is we are going to just draw some Lewis structures and go over some of the problems that we didn't get a chance to do in class. So I'm going to start with carbonate. So carbonate, it has carbon, which has 4 valence electrons, and 3 oxygen atoms, each with 6 valence electrons, so you have to count all of those. And it's a -2 anion, which means there's an additional 2 electrons in this picture. So if we do this, we have 3 times 6 is 18. 18 and 2 is 20, so there's 24 electrons that we have to show in our picture. So the way that we do that is we start with the central atom, and we draw single bonds to external atoms. Okay, so if we keep a little tally here, that's 24 minus 6. Notice that we have 3 bonds, so that's 6 electrons. So I have 18 electrons left to kind of sort out and put into this picture. So if I start filling in octets on my oxygen, notice each oxygen atom needs 3 lone pairs to accompany the two bonding electrons to give it 8 total electrons. So there's 8 electrons for this atom. There are 1, 2, 3, 4, 5, 6, 7, 8 for this oxygen atom, and 1, 2, 3, 4, 5, 6, 7, 8. But if I look at this picture now, 6, 12, 18. I've added an additional 18 electrons, which means I'm out of electrons. Now the problem with that is that carbon here does not have an octet. So I could put a pair of electrons on it, and that would give carbon 8 electrons, 1, 2, 3, 4, 5, 6, 7, 8. However, now this picture has 26 electrons, and it's supposed to have 25. I could erase 2 of the electrons on one of these oxygen atoms, but that doesn't do me any good. Why? Because now this oxygen atom just doesn't have an octet either. So even though this has 24 electrons, again, we don't have a correct picture. So the solution is actually quite simple. And the solution is that instead of having 2 electrons count only for the carbon, or before having these 2 electrons that were on oxygen only count towards the oxygen, we want them to count towards both, and that means they need to be shared and not lone pairs. So what I do is just erase, sorry, I'm over erasing things here, but that's okay. Erase that, put our carbon back, our oxygen back, and instead of having 1 bond, we have 2, and that would put 2 lone pairs on this oxygen atom, and that would be our picture. So notice now if we count things, we have 8 electrons here, we have 8 electrons here, that's 16, and we have 8 electrons total here, that's 24. So this picture has 24 electrons, and this is the correct Lewis electron diagram, or the Lewis formula, excuse me, for this anion. Now we will often sometimes put this in brackets and put a 2- charge up here, and that's just to remind you that this whole thing is an ion. It does have -2 charge for this whole thing. Now, you may say, well, why did you draw the double bond to this oxygen? Could you not have drawn it to one of the other 2? And the answer is yes. So if we could have drawn it just as easily with a double bond towards this oxygen and single bonds towards this 2. So this would be what we called a resonance structure or a resonance form. A resonance form is a different way of drawing a Lewis formula for the same arrangement of atoms. These are not isomers where the atoms are connected differently. These are resonance forms where we're showing the electrons in different places. Here the electron density is on this oxygen. Here we've got electron density here, double bond here. And there is a third way, of course, of doing this, which is C with a double bond to this oxygen. So again, we'll just draw these in really quickly, and you can see the resonance forms here. Now, how do we know which resonance form is best? This is not to say that any of these are wrong or any of them are incorrect because they are correct by the rules that we have established for Lewis formulas. Everything has 24 electrons. You can count this in all three of these pictures. And everything has an octet, 8 electrons for each atom. And you can count those in all three of these pictures. So how do we establish which is the best one? Well, in this case, there is no best one because all three are the same. All we're doing is rotating. If you can imagine rotating this 120 degrees clockwise, you'll get the same thing as this one and the same thing as this one. But we can do better than that. So let's write down the formal charges. So the way the formal charge works is you take the number of valence electrons that the neutral atom has. So this is for the neutral atom. And we subtract the number of lone pair electrons, and we subtract 1/2 of the bonding electrons. And this is the formal charge on each atom. Okay? So what does that mean? That means the lone pairs, so that means you count all of the lone electrons on an atom, and half of the bonding electrons means, well, take example this bond here, or this atom, this oxygen atom. Well, here's a bonding pair. That pair has 2 electrons. You only count half of those, so you only count the line as 1. So essentially what we're doing is we're counting each dot and each line. So that's the way that I do this. I look at the atom, I see how many valence electrons it's supposed to have. So this is carbon. Carbon's supposed to have 4. And this is oxygen. Oxygen is supposed to have 6. I take that and then I subtract the number of things touching it. The number of dots, and this half bonding electrons means the number of lines. So this part here is the number of dots, and this part here is the number of lines. So let's do these as an example. So here's oxygen. It's supposed to have 6, it's group 16, and we're going to subtract the number of dots, 1, 2, 3, 4. So there's the number of dots, minus 4, and then subtract the number of lines, 1, 2, so 6 minus 4 minus 2 equals 0. There is no formal charge on this oxygen. So what about carbon here? This central carbon is supposed to have 4 minus the number of dots. There are no dots on the central carbon, so we'll say 0, minus the number of lines, 1, 2, 3, 4. 4 minus 4 equals 0. What about these oxygen atoms? Well, let's continue on. So this one, again, is supposed to have 6. 6 minus the number of dots, 1, 2, 3, 4, 5, 6. 6 minus 6. And then minus the number of lines. There's one line. 6 minus 1 is minus 1. So this is 6 minus 7. That's minus 1. So there is a negative formal charge on this oxygen atom. And we get the exact same thing for this one. 6 minus 1 equals minus 1. And again, there's a negative formal charge on this atom. So if we do this for each of these, we'll find that in every case where we have a oxygen with 3 lone pairs and 1 bond, those always have negative formal charge. Okay. Remember, formal charges are not real charges. They're not like charges on ionic compounds. These are bookkeeping devices for us to kind of keep up with where the electrons are distributed in our pictures. Okay, the last thing is to notice that all of these are the same. They each have 0 formal charge on the carbon. They each have 1 oxygen with 0 formal charge and 2 oxygens with minus formal charge. By the way, also notice that in each one of these, when we add them together, 0 plus 0 plus minus 1, we get the overall charge of the ion. 0 plus 0 plus minus 1 is minus 2. 0 plus 0 plus minus 1 is minus 2. So formal charges better add up to give you whatever the charge is of the picture that you're drawing. Last thing is that the real molecule, the real ion in this case, is going to be a hybrid or a mixture of these 3 pictures. So if we wanted to try to draw what the resonance hybrid actually looks like, so what does this molecule actually look like? It looks like some kind of hybridization where we have all three of these possible pictures at once. Now I'm not going to try to draw lone pairs in here because the whole point of a hybrid scheme is that the electrons are not located in any one specific spot, but they're spread out over the whole molecule. And so for our resonance hybrid, what we would say is that we have three identical atoms, oxygen atoms, with three identical kinds of bonds. The bonds are not single bonds and they're not double bonds. They're somewhere in between, and the whole thing has a -2 charge. And this is what we expect our actual real picture of this ion to be like. And if we do the spectroscopy of this, if we look at the experimental data, what we'll find is we do in fact have three equivalent bonds, and that those three equivalent bonds are somewhat between a typical single bond and a typical double bond in terms of bond energies and in terms of bond lengths. So this is the correct real picture for carbonate. These are the three Lewis structures or Lewis formulas for carbonate, and those are called resonance forms.